In this lesson, Chapter 2, Section 1, we're going to be looking at basics of functions and their graphs. So I'm going to take you on a quick tour of everything that's contained within this packet, and then we'll go back and start looking at each of those items. Okay, an overview. What are we looking at when we talk about basics of functions and their graphs? We're going to start off looking at some terms and the definition of those terms with some examples of those terms. We're going to be looking at what determines whether or not we have a function. We're going to look at that numerically through ordered pairs. We're going to look at if a graph is a function, and we're going to look at if equations represent a function. After that objective, then we're going to look at some graphing notation and function notation. We're going to actually evaluate functions algebraically. We've had a little practice with that, and we're going to have some more practice with evaluating functions algebraically. Simply plug in x values. Okay, and then it continues over here. We still are going to look at graphs of functions. Then we're going to look at what's the domain and range of a graph. And we're going to use the notation, set notation or interval notation, to help us describe the set of domain and range. So we have a lot of information contained down here that we'll have to go through. Okay, with regard to functions, we're going to continue on the third sheet looking at domain and range using set builder and interval notation to describe those x and y values. We continue looking at domain and range. As you can see, there's a lot of information about domain and range. And then we're also going to be looking at other items with regard to functions. We're going to be looking at what is an x-intercept, what's a y-intercept, how do we report those answers, what's the notation we use to describe x and y intercepts, and then we're also going to evaluate functions from a graph instead of from an equation. All right, so going back to the beginning, let's look at our terms and our different definitions. So when we say we have a relation, that's any set of ordered pairs, pairs meaning two, and we usually represent an ordered pair by using parentheses, and then we have the first coordinate, which is oftentimes called x, and the second coordinate, oftentimes called y. We can use any letter of the alphabet to represent an ordered set of ordered pairs, but it's kind of common practice to use x and y. So a relation is just a set or a collection of ordered pairs that describe a point on a graph. So here's an example of a relation. So you can see within these outside braces, these symbols are called braces, they're kind of squiggly. Within there, we have three ordered pairs. We have x is 0, y is 0, x is 2, y is 4, etc. All right, so the notation around each ordered pairs are the set of parentheses, and that's required. Okay, what's not really required are these braces on either ends, the bookends here. It just kind of says, hey, this is the grouping, this is the set of ordered pairs. Okay, quick reminder, okay, a set of ordered pairs can be graphed on the coordinate plane. We can look at having an x-axis, that's the horizontal axis, and then we have a y-axis, that's the vertical axis. Just a quick review, if I'm going to plot the point, let's start with this one because this is kind of a special case. If I wanted to plot this ordered pair, this is the x-coordinate and this is the y-coordinate. We always start at the origin. The origin is right here where the two axes cross. So the x-coordinate tells us how far to move horizontally, left or right. If x is -2, I would step 2 to the left. But then I also have to travel vertically 4. So 4 being positive, I would move up 4, and I would put the ordered pair right here. Likewise, plotting the ordered pair 2, 4, again, restart at the origin, move right 2, and up 4. So right 2, up 4. And the last ordered pair that we're going to plot in this relation is the origin. So here we have discrete points. There's no suggestion that I connect these, not when you have a list of ordered pairs. Okay. What's the domain? Well, the domain is the set of all x values, also called the input value. So you kind of want to start to make a connection. If we say input, we're talking about the x's. We're also talking about the term domain. So we're asked, what's the domain of this relation? Well, all you do is you simply go in and you grab all the first coordinates, the x coordinates. So notice we have 0, 2, -2. It wouldn't be wrong if you didn't list them smallest to largest, but smallest to largest is usually the common practice way to record and report those domain values. So 0 to -2, that's going to be this list right here, but just in order from smallest to greatest. All right, so what's the range? The range is equivalent to the y values, also called the output values. So what's the range or the y values of this relation? Well, 0 and 4 and 4. We don't usually write the repeated values, so this would suffice right here. Notice something else, the notation. Notice that on either end of these collections here of numbers, notice these braces, those squiggle parentheses. Okay, that just suggests that in between braces, that these are the only numbers, not everything in between these numbers. These are the distinct numbers that are part of that domain or part of that range. All right, let's look at what a function is. A function is a set of ordered pairs such that each element in the domain, each x coordinate, corresponds to exactly one element in the range. That's not real clear, but we're going to work through this and hopefully make that clear. So we're going to look at determining if a relation determines a function, if a graph determines a function, and if an equation determines a function. So we're going to start out by looking at a set of ordered pairs to determine if those ordered pairs of that relation determines a function. That's called numerically. So a relation is kind of your general term. It's just a collection of ordered pairs. A function is more specific. That relation has to satisfy a set of criteria. And that criteria is that each x or domain only has one output value, one range. All right, so numerically, let's first of all look at, if I'm given a set of ordered pairs, a relation, does that relation also suggest that you have a function? So is y a function of x? So we've got two relations here. Okay, what's the description? There can be no repeated x values. Repeated y values are okay. So let's say this problem was presented to you and you're saying, hey, here's a relation. Does this relation define a function? Well, do I have repeated x values? Nope. So that means that yes, this collection of ordered pairs, this relation can now be called a function. Look at example B, 5, 6, and 6. I have repeated x values, so the answer is no. This set of ordered pairs would not define a function. So a visual for this to help us with our next objective is I'm going to take the set of ordered pairs in A and B, and I'm just going to quickly plot them so I can give you a visual of why, and another reason to think about why those relations do or do not determine functions. Okay, and you can just watch or you can write this down if you want to too. So I'm going to go to relation A. I'm going to plot these three ordered pairs on a coordinate plane. I don't want to be real specific. I just want to kind of get a general graph. So to plot 5, 5, I'm going to move right 5. I don't need to show every tick mark, and I'm going to move up 5, and I'll call this 5. And I'll put the point here. Now I'm going to plot 6, 5. Well, thinking about my scaling here, 6 would probably be here. Move up, I go up to 5. These points are lining up horizontally. That's okay. Let me plot the ordered pair 8, 7. So maybe the scale would have to be here, 8. And I'm going to have to go up a little bit further on the y-axis. So here's 8, 7. So when it says that each element in the domain corresponds to exactly one element in the range, what they're saying is go to every x. When you're standing at x equals 5, look up, look down. Okay, look up, look down. I only have one y value for the input of 5. Look at 6. Look up, look down till you find the point on the graph. Well, there it is. There's not another point that's lined up vertically when x is 6, so that means x equals 6 only has an output of y equals 5. And likewise with 8. X equals 8 only has one output of 7. So repeated y values are okay. So notice that in example A, I do have 2 points that have the same y value, but our eyes shouldn't even land, for this question, if this relation is a function, your eyes shouldn't even land on the y coordinates. The only thing you should look at are the x's, and if any of the x's are repeating for this question. Okay, let's look at relation B. Quickly plotting that set of ordered pairs. Again, I have 5, 5. Then I have 6, 7. So maybe that's about right here. And then I also have 6, 9. So when X is 6, not only do I have an output of 7, but I also have an output of 9. So this would not satisfy the requirement to be a function because this input value, X equals 6, has two different output values. The Y values would be 7 and 9. So that fails to be a function. So when you have repeated X values, visually what I want you to think about is that you're going to have 2 points on some graph that line up vertically. So this disqualifies this relation from being a function. All right, so we just looked at what determines numerically if we have a function. Well, we looked at the ordered pairs and we kind of have this background right here. Okay, I'm going to skip over because the order is better for me if I now go to, let's look at graphs and see if those graphs would satisfy a function. So we're going to go to page 2 and we're going to go to this part where it says graphs of function. So it's actually kind of right here that we're going to be focusing on. Okay, same objective, but now notice we don't have a relation. We don't have a numerical set of ordered pairs. Now we have 4 graphs to be able to identify if we have a function or not. All right, graphs of function. Identifying functions from graphs. These are all graphs, but are they specifically functions? It's kind of, equate this to a quadrilateral. That's a 4-sided figure. Okay, think about a rectangle. So when we talk about a rectangle, that's kind of general. But then when you talk about a square has more requirements to be classified as a square. All 4 sides of that rectangle have to be equivalent. So not every rectangle is a square, just like every relation is not a function. Kind of hope that helps. All right, let's identify functions from graphs by using what we call the VLT, or the vertical line test. If any vertical line intersects a graph in more than one point, the graph does not define Y as a function of X. Note open circles, closed circles, and arrows. Okay, well, my software program here didn't put these arrows on, so the graph does suggest that the arrows do suggest the graph continues. It's just I couldn't get the arrows on there. And likewise, we have arrows here at these ends and arrows here. These 2 graphs, well, this one might have arrows here and arrows here. Okay, so yes or no answer. Is this graph a function? Well, think about if you had a toothpick, or right now I just have a pencil. Okay, let's put our pencil vertically. This is a vertical line test to determine if I have a function of a graph. So I'm going to start from the far left and move to the far right. That's starting with small x values, moving to large x values. And as I move my vertical line or my pencil to the right, okay, there's no part of the graph right here yet. So I'm not even in this question until I start intersecting the graph. Okay, notice that in all places on the graph except for at x equals 0, your toothpick or your pencil, okay, when lined up vertically, it would have an intersection of 2 points. So for example, I'm intersecting the graph here at this top point and here at this bottom point. This is not a function. If you think about it, if I just said, and I can't really see the grid, but let's say this is like 5. If x is 5, then y is whatever this y value is when read from the vertical axis. And also my output when x is 5 could be this y value down here. So notice that just like on the relation, I have 2 points that line up vertically. This is not a function. So this is no. Okay, let's look at the circle. Does a circle define a function? Does this set of ordered pairs when graph define a function? No. For the same reason, we fail the vertical line test. Choose any x on the x-axis that's contained within the circle, like maybe right here at x equals -2. If x is -2, then my y can be this number, whatever it is when you slide it over to the vertical axis and read it. And x equals -2 can also have a y value down here at this bottom part of the graph. So you have 2 points that line up vertically. So your toothpick would intersect this graph in 2 points when held vertically. No, this is not a function. Take your toothpick and just start sliding it over. At most, how many times will you intersect the graph when you pause your toothpick? Well, just once. So that means that every x has only one output. There's no way you can stand at an x and get to two different y values. This, yes, by the vertical line test, is a function. All right, watch out. This one's kind of tricky, but it might be kind of hard to see, but these are all open. I think they're all, no. This one's a closed circle. This one's open. This is an open circle, and that one's a closed circle. So from far left to far right, at most I'm intersecting in one place. The point of concern is right here vertically, where you have this closed circle and this open circle. So let's say I'm standing at whatever x value that is. If I move upward, that's an open circle. That's not a point on the graph. But if I move downward, that is a point on the graph. I'm still only intersecting this graph in this one closed circle. Same thing if you continue. And here's another point where you want to another place where you might want to have some concern. Again, a toothpick when placed through here vertically is only going to hit that point because that's an open circle. It's not included in this graph. So yes, this is a function. This is sometimes called a step function because you can kind of see you're stepping up, you know. All right, so far, let's go back. We've looked at what is a relation. It's a set of ordered pairs. We've looked at the domain idea. That's the x coordinates of the points that are part of your relation. The range are the y coordinates. Okay, a function is a specific relation. It has to go through and meet certain criteria. You can only have one y value for every x value. And we looked at functions from ordered pairs numerically, and now we've also looked at functions by a visual of looking at a graph. All right, so we've looked at numerically, graphically. Now it's time to determine if a graph is a function by using the equation of the graph. So now we're going to go back to the front because this is the third part here. So this is the first way to determine from a set of ordered pairs if you have a function. This is the second way, graphically. Now, analytically, which means through an equation, can we determine if these equations, when graphed, determine functions? So, from equations, is y a function of x? So let's see what it says. If the equation is solved for y, okay, that means get y by itself on the left or right-hand side of the equal sign, and more than one value of y can be obtained from a given x, then the equation does not define y as a function of x. And then over here it says y must be degree 1. I'm going to change this. Y must be an odd degree. Typically in this course we just look at a power of 1, but I'm going to put down here y must, when you get y by itself on the equation, y must be an odd degree. And what that means is that highest exponent has to be an odd number in order for you to have a function. All right, so option A here, let's see. Does 2x plus y equal 6 when graphed determine a function? We're asked to solve the equation for y if it's not already done so. Okay. Some of you might see this as a linear function and you already know this, and that's fine. But if you're given an equation and you're trying to determine if y is a function of x, you go through this mathematical process. Let's get y by itself, which means I want to subtract 2x from the left side of the equation and also 2x from the right side. Now, I'm going to go ahead and cancel these. I'm left with y equals. Notice I didn't put negative 2x underneath 6. It's just to say that these are not like terms. So now let's take this that's in column format and let's rewrite it in a row. All right, a couple things to think about. Do we have an odd degree on y? We've isolated y. Well, y's understood exponent is 1. Let me think. Yeah, 1's odd. This must define a function. Okay, numerically, let's just do a little test on this. Okay, let's just choose any x for a given x. X can be, let's make it easy, 3. Or no, that's not going to give us 0. That's weird. X is 1. Okay, that's my given x. X is 1. When you plug in x equals 1, you're going to get negative 2 plus 6, which is 4. So if my input value is 1, my output value will only be 4. There's no way I can plug in 1 for x and get anything other than one y value of 4. So yes, this is a function. I chose 1. You can choose 0. You can choose a negative number to put in for x. It won't matter. You're only going to get one answer back out, one y value. Okay, let's look at example B. Well, already just by inspection, let's look at this equation. I see that y has an even power. I'm predicting that this answer is no, that this is not a function based on y must be an odd degree. All right, so how do I get y by itself and kind of mathematically determine that this is not a function? All right, let me get x squared out of the way, move it to the right side of the equation. Cancel those. I've got y squared equals. Now over here, I'm going to kind of arrange this in a row, negative x squared plus 1. I want to get y by itself, not y squared. So the next thing we do is we bring in the square root. So I rewrote the problem and I'm bringing in the square root. And be thinking, as you're bringing in that square root, in your brain you should be thinking, oh, that's an even root that I'm bringing in. So the square root on a square, an even root, takes the y out, but it puts absolute value around it because there's going to be 2 solutions. Now over here, I cannot simplify this. Okay, you can't simplify across a sum or a difference, only under a radical if you're multiplying. So what do? I just bring it down again. Okay, I'm going to come up here. Right, now it's time for me to remove the absolute value. So when I remove the absolute value bars, what that tells me is I have to make an adjustment to the right side of the equation and put plus minus in front of that radical. Mathematically, what we've just done is we've proven that when you plug in an x value for this x right here, that once you do this work right here, you're going to have to put a plus and a minus in front of whatever number that is. That's 2 different y values for that one x that you plugged in here. So the visual is the plus minus. No, this equation does not determine a function. All right, let's look at C. Okay, C is already done for us, meaning that y is already on one side of the equation by itself. I'm looking at y and I'm going, okay, well, y's understood exponent is 1. That's an odd number. So that must be that this is a function. And you'd be good to go. If you're not convinced and you want to, I was always wanting to investigate and go, are they really right about that? So choose a number to put in for x, a given x. I'm going to choose 3 to make the work easy. The square root of 4 then would be 2. And that's my only answer is 2. There's not a plus minus in front that would make that 2 anything other than just a 2. All right, let's look at D. Does this equation, when graphed, determine a function? Well, I see 2 y's in here, and they each have an exponent of 1. So I guess if I had to predict, I'm going to say, yeah, I think this is going to be a function. I'm going to kind of write it in lightly, not box it yet. Okay, I'm thinking, yeah, you know what? I think that's going to determine a function. Okay, how do I prove it mathematically? Let's get y by itself. Well, notice that you have 2 terms. The first term here and the second term here on the left side of the equation that both have y's in them. Let's go ahead and factor out that y because it's a common factor. Let's factor out the y from these 2 terms. When you factor out a y from this term, you're left with x. When you factor out a y from the second term, you're left with minus 3. Double check by distributing. Check your work by distributing the y back in to see if you get back up here to the original problem. Now I only have 1 y, and it's a factor. So this is y times this quantity. How do I get y by itself? Well, I want to divide out this parenthesis. Now it's kind of weird, but let's divide out this whole group right here to the left side of the equation, which means over here, I've got to also divide out x minus 3. Now here, notice I didn't put parentheses because it's really not necessary. You could put parentheses and it would not be wrong. So now, cleaning this up, I have this fraction right here. When I got y by itself, I see that I have an odd degree, 1. So I'm thinking this is a function. If I'm not convinced, let's come up with an x value that I can plug in right here to see how many different answers I get back. I wouldn't plug in 3 because if you plug in 3 for x, you're going to divide by 0, and that's a bad thing in math. Let's plug in 4 for x. Let's say you plug in this given x value of 4. Well, then you're going to have 6 over 1 when you subtract the 3, and my answer is 6. If you plug in 4, the only answer you're going to get out is 6. There's no way when you plug in x equals 4, you're going to get anything other than 6. So that input only has one output. So yes, this is a function as I predicted. A lot of information in just this small part of this, but just remember, we've looked at relations, a set of ordered pairs. We know the domain values are the input values, or the x's. The range are the y values. We have them listed kind of in a roster method here, okay, is what that would be called, a roster method, because we don't have an entire graph. All we have are these points that make up this graph. Okay. We looked at determining if a relation determined a function. We looked at it numerically from sets of ordered pairs. We looked at the vertical line test to determine if we had a function by thinking about using a toothpick to run across these graphs, looking for intersection points. And then what happens if they present me in my problem with an equation and say, hey, is that a function? Well, now we know the process to determine if an equation results in a graph that would be a function. All right, I think one more thing we're going to do in this video, and then I'll have to go to another one, is I want to kind of look at the bottom part of this page right here. Let's look at now some notation of functions. Remember, we're looking at basics of functions and their graphs, just ideas about graphs. All right, this is said right here to be in graphing notation, where you have y equals 2x plus 1. This is ready to be graphed, meaning I can choose x values, get y values, and then go to a coordinate plane and plot those ordered pairs to kind of see what that graph looks like. Yes, y is a function of x. All right, this is what we call function notation. Notice that we've replaced y with f of x, but everything else is the same here. So basically, it's saying that f of x is the same as y. If you know you have a function, which I do up here in this notation, instead of using y, I can use this f of x. That f kind of tells us that, hey, that equation is a function. It's just a different name for y. It's just like I'm Kim, I'm Mom, I can be Grandma, I can be Mrs. Fudge. Those are all my names, but I'm the same person. So y equals f of x, if you know you have an equation that represents a function, f of x can be used instead. I prefer this notation right here, and depending upon what I'm doing mathematically, sometimes I'll write my equation in this notation with y, and sometimes I'll use f of x. It just depends. All right, so evaluating functions algebraically, we're going to plug in x values. Okay, so that's our next objective. All right, so we get all this information right here is just some examples of that process. Okay, let's say you're given this equation and it says find the value of y when x is 6. Okay, plug in 6 here, we get 13. I got it. So we're just showing the process here. What if you're presented with this equation instead of y, but f of x, and it says find f of 6? Well, it's just saying evaluate the function. This is not multiplication. This is saying this is my input value. Think about this 6 being replaced in for this x here, but you also have to replace it in for all the x's in the equation. So now kind of put your eyes over here. See f of 6 equals, and all they're doing is plugging in 6 for the x. The answer is still going to be 13, just like I'm still the same person with different names. I just like this notation a little bit better. It describes what function I'm on, and the name of the function is f. As opposed to this, I don't know if this function has a name for it, f, g, h, or y. All right, so given this function, it is a function because when graphed, this will pass the vertical line test. It says evaluate f of negative 2. All right, I'm going to actually move up here. So I'm going to rewrite the equation. And I like to kind of be nice, neat, and organized. So it asks me for part A, right here, to find f of negative 2. So I'm like, okay, well, f of negative 2. So think about the change. Put your eyes down here like in a column format, okay, vertically. It's saying plug in negative 2 for x. Well, okay, I'll plug it in here, but then I also have to go into the equation, and everywhere I see x, plug in negative 2. So x is negative 2. I would put parentheses around that and keep the square on the outside. Plus, and then 3. This is times x, so I'm going to go ahead and use parentheses for multiplication. -2, and then -4. Why not go straight to the calculator, enter this in, being careful of parentheses around negative numbers. I think this is going to be -6 when you do all that work on the calculator. So when you plug in -2, your output, your y value, is going to be -6. And so another way to think about this is the ordered pair, when x is -2 and y is -6, this ordered pair would be a point on this graph right here. All right, so for B, same thing, but now in the original problem, new problem B is plug 1 in here and 1 in here. Notice how this is just nice. It's very evident of what we're writing down. So f of 1, I don't need to be mindful of parentheses for x because that's a positive number. And I believe this answer is 0. All right, so when the input value is 1, my output value, my y value is 0, which is another way to state that in ordered paired form is that the point 1, 0 is on the graph of f. All right, continue on the back side here. We have another, we have the same function, but now we're not putting in numbers, we're putting in expressions. So instead of plugging in a value for x, now it says, hey, everywhere you see x in this original problem, replace it with -x. And I know we're going long, but we're almost done with this objective, and I want to kind of finish this one up. So part C, it says f. Now, instead of x in the original problem, replace in, for every x in the equation, let's plug in -x. So being mindful, this is negative, so put -x in parentheses and the square on the outside. A lot of mistakes are made here with the inputs of -x. So notice what I'm doing. I'm just bringing this same expression down, equals. This is like your name, your label that you want to kind of bring down, and it's important. All right, what's -x squared? Well, -x times -x. I manage the two negatives, and because there's two of them, that's an even number, that negative is going to turn, that negative times negative is going to turn into a positive. Then I manage the variables. What's x to the first times x to the first? Well, properties of exponents say I have to add those. So quantity -x squared produces a positive x squared. Now let's do this multiplication. That's just -3x, and then I have -4. I'm finished with this problem. I have no values for x, so I'm done. If I wanted to write this in ordered pair form, it would be -x, comma, and then all of this would have to be my output, whatever my y is. So this would be the ordered pair format of that ugly problem. All right, and then the last one here, let me kind of come over here and manage it this way. I'm going to write down the original problem. And now I've noticed that in part D, now they want me to insert not a number and not just a one, term. They're saying now in between these two parentheses, my new x is x plus 1. So come over here. Okay, x plus 1 equals. So now all of this gets replaced in for these x's in the problem. So I'm going to take that square, put it on the outside, and I'm going to have x plus 1 plus 3 times where this x is, replace it with x plus 1, and then -4. So bring this side of the equation down. It's your label for what you're doing. As you can see here, now we're going to have to FOIL. So you can go off to the side, expand that, multiply x plus 1 times x plus 1, and I'm going to go ahead and do that quickly. When you FOIL and clean up, you're going to get x squared plus 2x plus 1. Now I'm going to distribute in this next group term, I'm going to distribute the 3, so 3x plus 3, and then -4. As a final step, I'm going to look to see if I can clean up anything over here. Well, I have only one x squared term. I see a 2x and a 3x, so that makes 5x. And then I look at the constants, and when I add these and subtract 4, I just get 0. So in that case, I'm finished evaluating the function at x plus 1. Okay, what does the ordered pair look like? Well, this is the x value. That's the input. I shouldn't say X value, it's the input. So that comes first in our ordered pair format, and this is the output. So if you're asked to write this notation in ordered pair form, that's what it would look like. All right, we'll continue in the next video with domain and range.